Thank you, Lance, for this very kind introduction. I'm really thrilled to be here and to present our latest updates here from our work. Um, Let me start by saying what the DCD is. So we are the German Center for Diabetes Research, which is a non-profit federal institute in Germany. We have 5 different partners, which you can see on the right side. And summed up, we have 450 researchers that are scattered from basic research up to clinical trials on patients. We have a variety of data. Usually it's very unstructured, extremely heterogeneous, it's not connected, and from a data perspective, it's very unfair. So fair means findable, accessible, interoperable, and reusable. Here you can see my team. So we are 4.5 developers. I would count me as 0.5 developer, and we're based in Munich at the head office in Munich. Our challenge in the DCD is to find the needle in the haystack. Problem is that we have a lot of haystacks, which should represent our data silos that are scattered across Germany. What we want to do is we want to answer easy questions. Sometimes they are very difficult to answer, but we also want to create knowledge and insights. Now the question here at Neo4j Connections is why we are using graph. Why not using relational databases? Well, the answer is pretty simple. Biomedical data, especially in healthcare, is highly connected by definition. So it makes a lot of sense to use graph technology to do that. It is very easy to model the data. With graph technology, we are extremely flexible, easy adaptable, so we can reshape the graph if we have something integrated and want to reshape it. This is way more easy than in SQL. We can scale up to billions of nodes. You can see that in a bit. The queries are very, very easy to write, even for non-computer scientists. And the cool new thing is Graph Data Science Library and graph embeddings, which allow us machine learning on the graph. So usually when we talk to our scientists, we have questions like that. Are human genes from GWAS studies type 2 diabetes enzymes acting on metabolites, which in turn are regulated in a pig model? So we have a couple of things here which you don't have to understand. On a data point of view, this question is A connected to R? And I have here an Excel sheet, which is one of our data sources here, and I give you 3 seconds to see if A is connected to R. So 21, 23, 23. Did you see that? I think not. I give you 3 seconds again, and to show you here if A is connected to R. 21, 22, 23. And I hope you saw that A is connected to R. It's very easy. It's very intuitive. And that's why graph technology is extremely well suited for our problems. When we get back to our data silos and Excel sheets and relational databases, we transform these into our graph. And this shows us here we have a graph problem, right? So we can connect here human data on genetic level, on protein level, on metabolite level, and we can even connect that to animal models and query data. Just to give you a quick detour here, diabetes is one of many connected diseases. We got stroke and heart attack as side effects. We got liver cancer, lung fibrosis as a side effect. Long-term complications are also Alzheimer's. So you see that diabetes is not a single disease. It's a connection of complex diseases that are interconnected with each other. And we try to find new hypotheses and new insights in that journal here. And that brings me to DCD Connect, which we call our Neo4j knowledge graph here. And what we do is we connect different locations from the DCD, different disciplines, different kinds of data, and also species. You see here animal models, you see human data, you see metabolite data, analysis data, insights, images, sequencing data, and so on and so forth. And we want to bring that all together so that our scientists can query that data much easier and much faster. So if we go from the inner circle to the outer circle, what we have here is DCD Connect, which is a knowledge graph, which is the core of our system, which is publicly available. And we enrich that using ontologies, infer data. For example, we infer data by using natural language processing techniques. And then we add another shell of information or data to it, which comes from our in-house data, for example, experimental data, clinical trials, and so on and so forth. How do we integrate data? Most of our scripts are Python-based, so we often use Python Neo as well as Graphio. Both are publicly available. Tim, our developer, wrote a very, very nice pipeline, which is also open source. You can see that here in his blog post to orchestrate our pipelines. And based on that integrated data, as I said, we annotate and enrich data. This is what we do using text matching algorithms as well as natural language processing. We infer new knowledge, and we also create shortcuts here, which you can see in this little graphic here on the right side. We integrated information from genes, RNA, and protein, and the gene is coding an RNA, and the RNA is coding a protein. So what we basically do is creating a shortcut here with this red relationship, and then we have one hop less to traverse through the graph. This brings me to the data model. We have a very simple data model, even if it's looking very complex to you and a little bit small. It is very human readable. It's easy to query. And this data model is created by our end users, which are medical scientists and non-computer scientists. And this is what they usually draw on whiteboards. And if we magnify that here, the very centric one is the literature database here in yellow, where we have abstract text that are connected to different terms from ontologies or connected to genes and proteins and transcripts, but also to clinical trials in chemistry and metabolites. Now let's go to the use cases that usually our scientists are querying. We start with the very easy ones, handling mappings of identifiers of molecular entities. Since we have many different databases integrated, and since biomedical data is very heterogeneous, people often give the same thing new names. For example, here, this diabetes relevant gene, TCF7L2. We can use a simple query as a one-line code. Here we are looking for a gene and also its mappings as well as the synonyms to another gene identifier. And you see here these roughly 15 nodes that are actually the same gene, but have different names and synonyms. So we can easily query that. Then we have the next thing. Since we include more and more data and connect these data silos, we can find information that is connected to it. Here we are querying for gene variants called SNPs, single nucleotide polymorphisms, that are associated to diabetes. And what we want to have an output is the relevant protein with its gene function. So what we're doing is we are querying the graph for diabetes. On the left side here, the gray node, which is connected to this single point mutation here in cyan. And this is connected to a gene here, again, TCF7L2, and its mappings, as well as its RNAs and the proteins. The protein is in green. And we see the terms from an ontology here in orange, and you see the ontology, which is called gene ontology. So we have standardized names for the proteins and the functions. Okay, these were the very simple ones. Now let's go to the more sophisticated use cases that we use and that we provide our users. We are transforming text into knowledge. We annotate data, as I said. Sometimes we enrich the data and the text information. And we come back to this very central point here, the abstract text. You see one of our 30 million abstracts that we have here. These are roughly 200 to 400 words, each and every abstract. And we try to classify that, and we try to find entities in these texts automatically. And this is what we're doing using Spacy, but also we use GraphAware to transform the text into a graph, do named entity recognition, and then connect these recognized entities here on the right side directly to the abstract. And you see on the left side here, color-coded, what kind of classifications these named entities are, for example, genes or eukaryotes or physical science things. And as I said, we connect that to the abstracts. And then we span a net in knowledge graph over 30 million articles. Next thing is more interesting. We use graph algorithms to infer new insights. We do a little detour here for a subset of COVID-19 data. In March 2020, so roughly a year ago, we collected 140,000 abstracts from COVID-19 related publications, and we did the same exercise named entity recognition on gene names. And then we ran a PageRank algorithm, which is already included in Neo4j, and we could identify ACE2 as the most relevant gene that is mentioned in all these 140,000 abstracts. And that was possible within, I think the query lasted for 4 seconds. And we could identify here this gene as the most relevant one, which is the surface protein that you might know from the mRNA vaccines. Fifth use case is using node embeddings to subphenotype our diabetic patients. This is a little bit more complex, and I guide you through that. What we also integrate here is in-house data from the DCD. So raw data, medical data of here 404 diabetic patients. We have the gender, the age, surgery, we have diabetes type, also medications, and we do a variety of experiments on these patients where we acquire parameters. Sometimes they are time series, so we also acquire the timestamp for that. In addition to the clinical data, we do so-called molecular fingerprints. And these are basically experiments where we can specifically measure here 116 specific lipids with the intensity. And on a transcript or on RNA level, 58,000 RNAs that we can measure from the patient's blood. So we have a fingerprint, we integrate that into Neo4j. And now the question is, which of the patients is more similar to another patient, or which is more likely to have the same response to the disease? And what we're doing here is fast random projections using the GDS library here. So we are transforming our clinical data, the fingerprint data, to the top 50 features here into a vector. And then we can use these node embeddings to cluster our patient data here in a subgraph. And we are using the integrated k-nearest neighbor clustering with k equals 5, because we have 5 different subtypes of diabetes in the literature. And our next task is now to interpret this data here and find new molecular markers for these subtypes that we calculated in Neo4j. So I showed you here how we integrate patients' data, and I showed you in the beginning of the talk the knowledge graph. And the cool thing is these are actually connected in the DCD. So we have the patient's data and we have the fingerprints here in cyan. And these fingerprints are directly connected to the literature, to the synonyms, to the abstracts, to the keywords, to the ontologies. And so we can quickly write queries to infer new data and to get more insights about these specific transcripts or lipids or whatever you have. The last use case is a very sophisticated one where we use graph integration, natural language processing, sentiment analysis, and GDS library. And we did this here with the COVID graph initiative, which is now called Health Echo. And I'm guiding you through that. So we used a data set by Meltwater, which collected press releases of clinical trials from COVID-19 clinical trials. And besides named entity recognition of the drugs here and of specific keywords, we also did a sentiment analysis. And this sentiment analysis should represent here as the traffic lights in red, yellow, and green. So whenever a clinical trial is rather positive, saying something about COVID-19, it's green. If it's negative, it's red. And we start on the right side. So what we did is clustering on the different drugs. And we see here on the right side hydroxychloroquine, which is clustered with only clinical trials that are neutral up to negative. And on the left side, we see clinical trials that are clustered around remdesivir, another drug. And you see that these clinical trials are rather positive up to neutral. And I don't want to judge this here, and I'm not a medical doctor, but I just want to show you here that we can use very, very sophisticated techniques, and within some hours of calculations or even some minutes, we can infer new insights and cluster our data. So with this, I guided you through the use cases that we have here in the healthcare sector. Just want to give you a short summary. We have our knowledge graph, which is the core and single point of truth, which we can connect here to our in-house data in the DCD. Everything runs really, really smoothly, so we can scale up that for billions of edges and nodes, and we can easily infer new knowledge using graph algorithms that are provided here with Neo4j. I showed you some use cases, the very simple ones where we have a one-line cipher query, a little bit more sophisticated where we use one or the other algorithm like PageRank or K-nearest neighbor. I showed you even node embeddings where we integrated patients' data, so medical data, to find communities and to find more similar clusters of patients. And I also showed you an example for natural language processing combined with clustering analysis in the last use case. With this, I'm at the end of my talk. I want to say thank you to the Federal Ministry of Education and Research and to all the other members here that provided a lot of insight, a lot of help. Really, really cool people. I love the graph community, and I hope you got some new information here and some interesting ideas that we are doing in the DCD. And I'm happy to take questions. And thank you very much for your attention.
Great. Thank you so much, Dr. Jarasch. You are doing such amazing work, and I love to see this. I was enthralled the whole time listening to you talk about the use cases. I mean, just great work. Thank you.
Thank you very much.
So I want to remind the audience, if you'd like to submit a question, you can do so by typing it into the questions tab located at the top of your screen. We've had a couple questions that have come in throughout the presentation, so I'll start with those. So here's one that's asking, is the graph publicly available?
That's a very good question. Yes and no. So the knowledge part, so the part of the public data, this is publicly available. When it comes to our connected in-house data and to our insights that we have in the DCD, obviously that's very sensitive data. So this one is not publicly available. And this is what we keep apart from each other using the role model of our enterprise license.
Great, thank you. And here's another one. It's asking, how big is this graph? And I'm assuming, I'm not sure which graph they're referring to, but how big is this graph in terms of nodes and relationships?
Yeah, so this is the question I often get. When we are talking our productive system, we have currently 300 million nodes and 1.1 billion edges. We have a developer instance, which is 1.1 billion nodes and 4.8 billion edges. So yeah, so this is running on a decent machine, 24 cores, 256 gigabytes of RAM. So no cloud system needed, very fast and responsive. Yeah.
Oh, great. That's great to hear. And I know we're running short on time, so I want to let the audience know if your question wasn't answered, someone from Neo4j will reach out to you directly, or you can send an email to webinar@neo4j.com and we'll get you pointed in the right direction. But I will ask this last question before we go. So what is the biggest challenge you faced when you implemented the various use cases?
Yeah, that's a tough question, actually.
Oh, good. I like when they're
yeah.
I like when they're tough.
I think the challenge is we have research data, and this is very different to, let's say, standardized data from automotive or from insurances. So we have very, very heterogeneous data. So we have very, very ugly unstructured data. So the challenge here is to integrate that into Neo4j and to clean that in a way, and also to understand that so that we can use easy queries, right? So I think this is the biggest challenge.
Great, thank you. And see, that didn't seem so tough to answer. Seems all right.
Thank you.
And Dr. Jarasch, I want to thank you so much for your time. It's always a pleasure having you here. We really appreciate you being with us today. So thank you. And
thank you very much for having me.
Oh, absolutely. And to our audience, our next session will be starting in just a few minutes. So stick around for that. Thanks so much.